In this example, we have a mass of a half kilogram of ammonia. It's contained in a piston cylinder assembly, so let's sketch that out. So here's our cylinder with the piston, and inside here we have ammonia. That's going to be our system. And we're told that it's initially at a minus 20 degrees Celsius and a quality of 25%. So that's x1 is equal to 0.25. Since we're given it that it's a quality, we're going to know that we're dealing with a superheated vapor. I'm sorry, a saturated liquid vapor mixture. So saturated liquid vapor mixture phase. Because we're given some quality, we know that that's the case. And then we're told the ammonia is slowly heated to a final state where the temperature is, so this is state 2. The final temperature is 20 degrees Celsius, and the final pressure is 0.6 megapascals absolute. So we know that we have some heat coming into our ammonia in our energy flow diagram. We also know that there's some work going on as well because we're dealing with a piston cylinder arrangement. We're told the pressure varies linearly with specific volume during this heating process. We'll make use of that later. And there are no significant changes in kinetic or potential energy. So for the ammonia, show the process on a PV sketch. We'll probably do that somewhere a little bit later into the process, since we're first going to need to calculate what the property values at the different states. Evaluate the work done by the ammonia. That'll be PdV work, since we're working against a piston. And then evaluate the heat transfer into the ammonia. That will be a first law analysis, because the first law involves the heat transfer term. From part B, we'll have evaluated the work term, and we can get the internal energy from determining the properties at state 1 and state 2. Okay, so that's an outline of where we're headed. So the first thing to do is figure out the properties at state 1. We're given the temperature there, we're given the quality. So let's calculate what the specific volume is and the specific internal energy. The reason I want specific internal energy is because we'll use it in the first law for evaluating part C of the problem. So since it's a saturated liquid vapor mixture, we know that to find the specific volume in state 1, it's going to be 1 minus the quality at state 1 times the saturated liquid value for the specific volume, state 1, plus the quality at state 1 times the saturated vapor specific volume at state 1. And similarly, we'll do the same thing to find the specific internal energy. So in order to do those calculations, we need to figure out what the specific volume in the saturated liquid and vapor states are. So let's write this down. Same thing for the specific volume. I'm sorry, for the specific internal energy. So I'm getting my words all mixed up here. Okay, so we need to determine what the specific volume is in the saturated liquid and vapor states, and what the specific internal energy is in the saturated liquid and vapor states. So to get these, we're going to go to the property tables for ammonia, and we'll look at the one organized according to temperature, since we're given a nice round temperature there. So minus 20 degrees C, so let's go to that. So here's a table for ammonia. It's organized based on temperature. We're dealing with minus 20 degrees C. So first of all, we can get the pressure. So that pressure is going to be 1.9008 bar. We can also get the saturated liquid specific volume and the saturated vapor specific volume. And similarly, we can get the saturated liquid specific internal energy and the saturated vapor specific internal energy. So let's try to remember those numbers, and then we'll write them down up here. So the specific volume is the following. It's going to be 0.0015035. Some numbers, unfortunately, just because we have to deal with table values. For this saturated vapor specific volume, it's 0.62373 cubic meters per kilogram. Specific internal energy in the saturated liquid state is 89.095 kilojoules per kilogram, and this specific internal energy for the saturated vapor is 1299.9 kilojoules per kilogram. And again, these come from the tables, from the saturated liquid vapor mixture table. Okay, so we can then plug those values in, and what you'll get is the specific volume at state 1 comes out to be 0.157060 cubic meters per kilogram, and the specific internal energy at state 1 is 391.796 kilojoules per kilogram. Okay, so we now know some of the other important properties at state 1. Now let's go to state 2 and evaluate the properties there. Now, state 2, we're told we're at a temperature of 20 degrees C and a pressure of 0.6 megapascals. So let's go back to the ammonia property table organized according to temperature. We'll use temperature since it's a nice 20 degrees. So we go to that one, 20 degrees is right there. And one thing you notice here is the saturation pressure is about 8.57 bar, okay, which is that's going to be about 0.8 megapascals, okay? If you look at that for a second, that's actually bigger than the pressure here. This, if you put it in terms of bar, this will be 6 bar. Okay, so the P saturation at 20 degrees C is the let's go back down here, 8.5748 bar. So we see that that pressure is larger than our P2 value. So what that means is that the pressure is larger, we're compressing, so to keep it in a saturated liquid vapor mixture state, you have to have a larger pressure than what we currently have. So that means there's less pressure kind of holding them, pressing against the material, so it's going to be in a superheated vapor phase, since the pressure is actually lower. So state 2 will be a superheated vapor because the pressure is lower than the saturation pressure at that given temperature. Right? We're not holding as much pressure on it, so it'll be more likely to become a vapor. So to find the properties for state 2, we can just use the fact that we're at 20 degrees C and 6 bar, and then go look at the superheated vapor tables for ammonia. Okay, so remember 20 degrees C and 6 bar. So here are the superheated vapor tables for ammonia. So we go to the 6 bar part of the table, which is right here. So here's 6 bar. Right, that's 0.6 megapascals. And we said that we're dealing with 20 degrees C, so that's right there. So here are the property values. They should be, here's the specific volume, and there's the specific internal energy. Okay, so we'll remember those numbers and write those down up above. We just have to scroll back to where we were. Okay, so the specific volume from the table was 0.22151 cubic meters per kilogram. Specific internal energy is 1348.8 kilojoules per kilogram. And these come from the superheated vapor table. And again, the reason is the saturation pressure at 20 degrees C is greater than our given pressure, so that's going to put us in the superheated vapor phase because we're not pressing in on that material, and because we have a lower pressure, it's more likely to be in a vapor state. Okay, so now we have the properties. What we'll do is now we can go ahead and show the process on a PV sketch, so we now know what the specific volumes are and we know what phases we're in. So let's just do that sketch down here. Specific volume on the horizontal axis, pressure on the vertical axis. We'll draw our vapor dome. State 1 was at a, let's see, I guess I didn't write down the pressure for state 1, so let's get that as well. So P1 is the saturation pressure at T1 equals minus 20 degrees C. So just going back to the table, that saturation pressure is 1.9008 bar. So state 1 will be somewhere down here, 1.9008 bar. And we know that's in the saturated liquid vapor mixture phase, so it's under the vapor dome. So let me just draw on an isotherm corresponding to that one. This is the T1 of minus 20 degrees C. And we're somewhere in here. Let's just go ahead and put it right there for state 1. There's our specific volume for state 1. State 2 is at a higher temperature and a higher pressure, 6 bar, and we know it's in the superheated vapor region. So let me draw that pressure somewhere up here, 6 bar. And let's draw the saturation isotherm for that one. Or actually, I won't do that. Let me draw the isotherm corresponding to the 20 degrees C for that one. Let's do that. That looks like this. So there's our state 2. This is the temperature T2 of 20 degrees C. This pressure here is that pressure of 8.5748. That's the saturation pressure for that 20 degrees C, 5748 bar. If you want to know what the isotherm is corresponding to this one at 6 bar, we could just go back to the pressure table for ammonia, which would be this one. Here's the table organized according to pressure, and for 6 bar, the corresponding saturation temperature is about 9 degrees Celsius. So that would be this isotherm if you wanted to sketch that one in. So that would be about the 9, what did I say, about 9 degrees Celsius. I can't remember the full decimal, but that would be that the saturation isotherm corresponding to 6 bar. But we're really at 20 degrees C, so we're out here in the superheated vapor region. So now we're also told that the process here, the pressure varies linearly with specific volume during this process. So the path going from 1 to 2 will just be a straight line. Right? Because we're told the pressure varies linearly with specific volume during the heating process. So that means it's a straight line from state 1 to state 2. So that's what that path looks like. Now we're asked to evaluate the work done by the ammonia during this process. So that's going to be our PDV work. So the work done by the system, which is our ammonia, will be the integral of P dV. And I'm going to write it as a specific volume as we go from specific volume 1 to specific volume 2. To get the work, I would just need to multiply this by the mass. Right? If you take mass times specific volume, that gives you the actual volume. Right? So I'm just going to leave it as specific volume here because I have a specific volume at 1 and specific volume at 2, and then to convert this to the actual work rather than work per unit mass, I just multiply by the mass. And the mass is given, right? The mass is given right up here as 0.5 kilograms. Now, to evaluate this integral, I could write out that, pressure as a function of specific volume as a linear function. I could write that out like this. So pressure would be like P1 plus the slope, which would be what? P2 minus P1 all over V2 minus V1 times V minus V1. So that's corresponding to this linear curve here. It's just the equation of a line. This is my starting point at 1, so P1 and V1. And then the slope of this line is just the change in pressure over the change in volume, or specific volume, just because it's a line. So I could take this and I could substitute it into here and evaluate the integral. So I could do that totally fine. That'll work. Another way to go that perhaps is a little bit easier is to just recognize that the work in going from 1 to 2 is just going to be the area under the curve. So the work is going to be correspond to this area that I'm going to shade in. So I'm just shading in the area underneath that curve. So I can do this geometrically. So if I can figure out what that area is, it's going to be the same as this integral using that. Okay, so the way I'm going to do that is I'm just going to take the average pressure between 1 and 2 and then multiply it by the width here. Okay, so that in other words, this will be mass times the average pressure, which would be P1 plus P2 divided by 2. So that puts me somewhere like right there, multiplied by this width. So that would be V2 minus V1. And then, of course, I have the mass here that I multiply the whole thing through by. Okay, so it's just a more geometric way to calculate the work, just based on using the area under the curve. So I could either, again, use this and substitute it into there and evaluate it, or in my case, I just did it geometrically. Regardless, I have all of these pressures and specific volumes, right? So P1 is here, P2 is right here. Specific volumes at 1 and 2, we calculated those. Sorry, these should have been 2s rather than 1s. So I have these. So I can plug it all in and I'll get the work done by the ammonia in this process. Comes out to be 12.7 kilojoules. Okay, so that takes care of parts A and B. Now let's do part C, evaluate the heat transfer into the ammonia. So for that, I'm going to use the first law applied to the ammonia. So that'll be the change in the total energy of the ammonia, which is our system. It's equal to the energy we put in via heat transfer minus the work done by the ammonia on the surroundings. This one we just calculated, that's 12.7. The heat term is what we're trying to evaluate. The change in total energy is, of course, the change in internal energy plus the change in kinetic energy plus the change in potential energy. But we're told in the problem statement to neglect changes in kinetic energy and changes in potential energy. Those are reasonable assumptions because as this ammonia expands, we're going to assume that it does so very slowly. So the kinetic energy of the ammonia doesn't change very much. It's always basically zero. And even though we are changing the elevation of the ammonia, I'm assuming it's moving the piston upward. Who knows, it could be moving it horizontally. But regardless, the change in elevation is either zero or very small. That's a reasonable assumption that the change in potential energy would be either exactly zero or close to zero. So that leaves just the change in the internal energy. The change in the internal energy is going to be equal to the mass times the change in the specific internal energy. That's the little u2 minus little u1. So we know these values. The mass is given as a 0.5 kilogram. U2 we calculated, or at least looked up in the table. U1 we looked up in the table. So we have those values. So when you plug in all those values, you can find the energy into the system or into the ammonia. The heat transfer, that'll come out to be 491 kilojoules, out to 3 significant digits. So there is a lot of energy going in. So the picture here is showing it going into the ammonia. So there's a lot of energy going in there, and that causes an expansion because the work is positive, so it means we're doing work on the surroundings. Okay, so just to kind of recap this problem, it involves looking up some properties, and that means making use of the saturated liquid vapor mixture table. We also had to use the superheated vapor tables. We had to make use of the quality to do some calculations to find the properties. So just some tedious work here, but hopefully that all seems straightforward. For state 2, probably the tricky bit there is to recognize that we're working with a superheated vapor, and the key to that was noticing that the saturation pressure corresponding to the 20 degrees C is larger than the pressure we're given. So that means that the material, the ammonia, would be in a superheated vapor phase. And then we had to use the correct table for that. Sketching it on a PV plot, hopefully you're comfortable with that, getting the correct isotherms and showing where the states are. The path from 1 to 2 we were given as being linear. We made use of that in calculating the work. The work is just PDV work. I did it in terms of a specific volume, so I multiply by mass out front to make it a volume. And you could either plug in the expression for how the pressure varies linearly with specific volumes. Totally fine, it'll work. It's a little more tedious. Or do what I did and just make use of the fact that the work is the area under the PV curve. So I just took the area under this. So it's a triangle plus like a rectangle. So I just used the average value for the pressure between 1 and 2, which is right there, multiplied by the width, which is right here. And then to find the heat, I just made use of the first law of thermodynamics, recognizing that the change in kinetic and potential energies are 0. Okay, we'll end the example there.